If you ever used an AI agent, you might have observed its failures. I, for example, use coding agents in my daily job. From time to time, they spit out some JSON that wasn't supposed to be there and get stuck. When this happens, most developers blame the model. But the real problem lies in the agent harness, not the model. But what is an agent harness? This is a term formalized by Michel Hashimoto in early 2026 and means everything in the agent except the model. Thus, agent equals model plus harness. In other words, the model is just a brain of an agent, and the harness is the body that allows it to interact with the outer world. The model is just a function that accepts some input and returns output based on the input. It has no memory and cannot actually do anything on its own. It is the harness that decides what input to pass to the model and what to do with its outputs. Just as a physical body gathers sensory signals, passes them to the brain for interpretation, and then physically reacts, the harness gathers context, passes it to the model, and executes the instructions. Understanding what a harness does is a prerequisite for building bulletproof agents, because the harness is the part that determines whether the agent actually works. Every agent harness does three essential things. First is context engineering, which dictates exactly what the agent sees at each turn. Every model has a fixed context window, and context engineering is the process of intelligently packaging all the essential data, like conversation history, tool definitions, and tool outputs, into that limited space. For instance, the agent harness has to decide when and how to compact the message history. If this is done incorrectly, the agent loses track of critical information and starts hallucinating. Second is tool orchestration with guardrails. This controls what the agent can do and what it shouldn't. Harness has to tell the model what tools are available without polluting the context. Then, when the model decides to call a tool, the harness has to actually call it. But before doing so, it has to check whether this is safe. In the end, the harness has to validate the tool output and forward it to the model. This is a very fragile part of the harness. Imagine a tool that calls some remote API. That API might face a temporary downtime. Harness should handle that gracefully. Otherwise, it might leave the agent hanging or hallucinating. In the worst case scenario, an agent might decide to call some dangerous bash command that the harness should block. Third is lifecycle and state management, which tracks what happened and where the agent is in a long task. The model itself is stateless. It doesn't have any track of previous interactions whatsoever. We can think of an agent as a state machine. When a user interacts with it, it goes into some flow. It communicates with the model and runs tools back and forth until it reaches a desired result and responds to the user. When the harness fails in this, the agent may stop responding, waste tokens unnecessarily, or simply not be able to accomplish a task. If you skip any one of these functions, the agent fails past a certain complexity threshold. To see how this three-part architecture plays out in the real world, let's look at three harnesses you might have already encountered. First is Claude Code by Anthropic. For context engineering, it dynamically compacts large code bases and message histories so the model doesn't drown in irrelevant data. For tool orchestration, it implements strict guardrails around local execution, actively pausing to ask for human permission before running potentially dangerous bash commands. And for state management, it orchestrates the back and forth loop of writing code, running tests, and reading errors until the specific task is complete. Second is Hermes Agent by Now's Research. Its context engineering relies on persistent memory, retrieving only the exact skills and data needed for the current prompt. Hermes has lots of built-in tools organized into toolsets that can be enabled or disabled. For state management, it runs persistently across sessions, meaning the state machine doesn't just reset to 0 when you close the chat. The third example is Mastra. a framework that gives developers the tools to build their own agents. For context engineering, it provides configurable memory management. For tool definition, it uses ZOT schema validation. This guarantees that tool inputs and outputs are correct. It also provides a library of guardrails to secure the agent. For lifecycle and state management, it uses a deterministic graph-based workflow engine. They all look different, but they prove that context, tools, and state are real diverse infrastructure problems that you cannot simply solve with a bigger model. So where does memory fit into this? We've already seen that the memory is part of the harness, not the model. It lives right in the context engineering and state management layers. A harness with no persistent memory starts every session from zero. Good memory management can improve not only output quality, but also performance and cost efficiency. Agent harnesses often use vector databases. One example of such database is Action Vector AIDB. You can now define an agent harness, name what it does, and identify examples. Most importantly, you have a clear framework for diagnosing why your agent fails and which layer to fix. Stay tuned for the next videos to learn how to apply this knowledge to solve real-life problems using Mastra and Vector AIDB.